is Camila, and my partner Gabriel and I will be talking about a replication control protocol called Gossip, also known as Epidemic. This protocol is widely used by distributed systems today to make sure that data is getting disseminated to all nodes on a network. But before talking about the Gossip protocol, I wanted to do a review on available copy protocols. As you may recall from last lecture, Gossip architecture, Gossip protocols are part of available copy protocols. These protocols provide the highest data availability and data reliability of all replication protocols that do not regenerate failed replicas. However, they do make a big assumption that network partitions are either very unlikely to happen or unlikely to cause conflicting updates. This, as we saw last week, can cause network partition problems. A common feature of all replication control protocols is the use of metadata to record the states of the replicas. And the way they do this is that they keep a version number that is an integer that gets incremented every time the replicated data gets modified. Okay, so what is a Gossip protocol? The Gossip protocol is a type of available copy protocols that supports file transfers between hosts on a network. And what's key in this is that it does it over decentralized networks. This protocol is based on the way viruses or rumors are spread. As you know, rumors in societies can travel very quickly and reach almost every single member of the community. And most importantly, they don't need a central coordinator. And this is what makes Gossip protocols scalable and fault tolerant. Similarly, according to epidemic theory, starting with a single infected individual, the time to infect the entire population is proportional to the log of the population size. And one clear example is the coronavirus, and I've included a time lapse of how quickly it spreads throughout the entire world. So what is Gossip trying to solve? In distributed systems, you need to know sometimes when other nodes are dead, you need to know when nodes are becoming alive, you need to get information about other nodes so you can make local decisions like knowing which node should handle a request. You need to learn about new configuration data and agree on data values and so on. So this is what Gossip is trying to solve. It's trying to solve the multicast problem, which is how do we get information from one single node to the rest of the network? And although you can use a common centralized approach, which is this one, which is to have a centralized server like a database and all of your other nodes query it for information. However, this actually introduced a lot of availability and performance issues for large distributed systems. And so instead, a Gossip protocol is simple in concept. Each node sends out some data to a set of other nodes. This data propagates through the system node by node, kind of like a virus, and eventually data propagates to every single node in the system. And this is what we call convergence. And to explain this, I am going to show you a simulation. So let's assume that we start off with 40 nodes in our network and we set fan out to 4. Fan out just is how many nodes an infected node will send its message to in every single cycle. So in the very first cycle, we expect that this node can infect 4 other nodes. Great, that is what we see. We see 1, 2, 3, 4 nodes getting infected after the first cycle. And if we fast forward, we notice that this keeps on repeating until all of the nodes in the network become infected, or in this case, red. And as we can see here from this simulation, the nodes in the network were able to reach convergence after 3 cycles, which is very close to the theoretical number of cycles. Now let's say that instead of 40 available nodes, we actually have 120 nodes in our network. We'll keep fan out to be 4. And what I want to demonstrate, what I guess I want to see, is how many cycles it takes when we increase the number of nodes by 3. So I'm going to hit play and let the simulation do its work. And as we can see, the number of nodes infected increases exponentially after every single cycle. And there we go. As you can see, the number of cycles that it took for all of the nodes to become infected when we have 120 nodes was only 5 cycles. This kind of proves the point that gossip protocols are scalable. In general, or hypothetically, it takes O log n rounds in order to reach all of the nodes. And if we keep on increasing the number of nodes, we won't see that big of a difference between. As we saw in the simulation, in each round, every node contacts another node at random, and it either receives or it can transmit a piece of information, or it can do both. So these are the 3 basic messaging strategies: push, pull, and push and pull. In the push algorithm, each informed node randomly picks another node and sends its message or update, whereas in the pull algorithm, each uninformed or uninfected node randomly picks another node, and if the selected node has information or is infected, it receives its message. And lastly, the push and pull is a hybrid. So in push and pull algorithms, all the nodes pick another node at random and exchange their message if either node is informed. We noticed that a lot of the papers preferred using push and pull algorithm, and the reason behind it was highlighted by the Karp et al. Paper, which showed that the number of transmissions or the number of cycles can actually be reduced significantly when the rumor is sent in both directions. That is, when using both push and pull rather than only push operations. Gossip algorithms have been proposed and are used nowadays for many distributed applications. In general, they're used in applications where consistency can be lazy, meaning that it's not crucial that all nodes see the same data at the same time. However, what they can count on is high partition tolerance and high availability when they use gossip protocols. Some of the applications that Gabe and I found online of the gossip protocol is database replication, and we see Cassandra being one example of using gossip protocols to do that. Gabe will be talking a little bit more about this. Another practical use is information dissemination. So how do we get one node to communicate to the rest? Cluster membership, and also failure detectors. And another company that uses gossip algorithms is Amazon S3. Some advantages of gossips are they're highly scalable. In general, it takes O log n rounds for a message to reach all the nodes in the system. They're also highly fault tolerant, as we were discussed earlier. They are robust, meaning there is no node that plays a specific role in the system. Therefore, if a node fails, it will not prevent other nodes from continuing to send information to the system. So this implies that a node can just join and it can leave whenever they please without disrupting the quality of the service. They can also offer convergent consistency, and as we saw in the simulation, the information is spread exponentially. And it's also a very extremely decentralized form of information discovery. And lastly, they actually are very simple algorithms, and they require very little code compared to other algorithms. Some of the weaknesses of gossip are they're not very efficient. Messages can arrive several times to a node, and this redundancy consumes most of the bandwidth. And we kind of saw this in the simulation where our actual number of cycles was a little bit higher than the theoretical number of cycles. Gossip protocols are also slow compared to multicast. The average rate to send a message is 1 over log of n. We also have latency problems. Because this algorithm is periodic, if a message has a new message, it won't be able to send it until the next cycle. And that adds to normal latencies like network latency. It's also very hard to reproduce and debug given the randomness nature inherited with these algorithms, so you can expect a lot of problems that arise during runtime. And finally, most of them rely on non-scalable membership protocol. And now Gabe will be explaining a little bit more about the gossip architecture.
Hi all, Gabe Acuna here. Gossip architecture is frequently used because of its ability to provide highly available services. We defined high availability by basically systems that are dependable enough to operate continuously without failing. And C, gossip architecture establishes a cluster of information held within replica managers, here represented as nodes. And every replica manager seeks to have the most updated information on all of the nodes in the cluster. Now, although having the same information seems redundant, it's actually the very reason we can have high availability, and this redundancy is commonly seen within other highly available systems. See, for example, let's say that the front end needs to get information or update information, but it happens to pick a state machine that is currently at a blocked or just in general failed state. We can just ping another one, and let's say this one. That is fine and it is stable, and then just continue the service. Therefore, even with failures within some nodes, the Gossip system maintains high availability. Now I'll dive a little more deep into the weeds of how the system actually works by explaining the subcomponents of the architecture itself. So to the left here is a very high level visual of how the architecture lays out. And something to note here from the get-go is that Gossip lays out the front end as the middle ground between the information itself and the client. Based on academic papers that we were reading regarding concept abstraction of Gossip architecture, the client does not know whether there are 2 nodes or 300 nodes. It just trusts that the service inputs and outputs correctly. Thus, in regards to abstract concepts, the client sees Gossip as a black box system. The client sends a query request, as we see here, and is returned a value. Or it can send an update operation, but at the end of the day, the real work is really, it's done here, not by the client itself. Now on the right hand side, we have the representation of the replica managers, who I've also been naming nodes interchangeably. Specifically just this rectangle right here that we'll be focusing on. So taking a look at the components, we have the value, which is here, which gives us information regarding the application state. Then we have the value timestamp, which is a vector holding the series of updates applied that have led to the current node value, which is right here. And then we have the replica timestamp, which is a vector that keeps only the stable updates that have been accepted by the replica manager within the update log, which is here. And then, which is what I would say is probably the most important piece of this is the update log right here. The update log keeps all updated operations tried on this replica manager, not just the ones that have been applied. So we need this to make sure that the replica manager is stable in regards to consistent update ordering before being updated. If we see that we're not currently stable, we hold the replica manager from updating. The other use for this log is to know whether or not the update has also been received and accepted by other nodes. If we can and have safely updated the current node, we still want to propagate the update through Gossip messages around the cluster that haven't done so already. Here we also have the executed operation table right here. And the executed operation table is kept so that the same update isn't applied twice. So we cross-check this table before adding an update to the log. And finally, we have the timestamp table right here depicted. And the table contains vector timestamps for each other replica manager that has came from Gossip messages. So when an update is applied to all replica managers, this table is used. Now I want to go forth and talk about what exactly are these Gossip messages moving around the cluster. Replica managers send what are called Gossip messages in order to bring other nodes in the cluster up to date. A Gossip message contains a node's update log as well as its replica timestamp vector, as denoted here by this portion, and obviously here. And once a replica manager has received this message by any given node, it has 3 main tasks to do now. The replica manager must begin by merging the log received by the replica manager's log, the one that it received, with its own log, keeping the best information from both the current and received. This is done by cross-checking both timestamp vectors and keeping the newest information. Higher values within vector timestamps mean newer here. After we have merged, the replica manager will process a set of stable updates from the update log. Having this set of updates, the manager applies them to its own value in the same timestamp order as they were previously applied in other nodes. Finally, this replica manager will check for records in the update log that have already been received by every other node, meaning that this would technically be the very last node to receive the update. And once it finds these records, they're cleared from the update log and execution operation table in order to aid in redundancy reduction. Now that we understand replica managers and Gossip messages, we're going to take a step back into understanding the actual operations that the front end requests from this cluster infrastructure. The most basic of the 2 types of operations in Gossip are queries, which are read-only. A query request, denoted as lowercase q, contains a description of the operation as well as a timestamp, denoted as q.prev. here, and here. Don't worry about this. I'll explain this in a second. The timestamp denoted as q.prev will basically send the latest version of the value that the front end thinks exists. Now, due to the relaxed consistency we see between replicas within this architecture, as they're updated constantly until eventually all receive the updates, the front end typically chooses a node randomly, and it will continue communicating with that node until it becomes unreachable. And this typically happens when the node is blocked, as I previously explained. And so this would be the communication. Now, when the replica manager receives the request, it submits it into a list of pending query operations until it can assure that all of the values within the value timestamp vector are greater than, meaning newer than the front end has previously seen, or equal to the timestamp vector values. This is what you're seeing here. And which is explained before, these vector values show the latest version of the value that the front end has previously seen. If it can't fully fulfill this condition, the manager waits or requests for the missing updates from other nodes. Now, once the node can assure that this condition passes, it sends back its value timestamp to the front end, and the front end merges it with its own separate timestamp storage, now having the most updated information to be eventually sent back to the client. Now, note that the front ends need their own vector timestamps separate from the cluster so that the ordering of operations isn't messed up by the cluster of nodes. This is which is displayed here. Gossip architecture has two forms of operations, one which is query operations, which we already covered, and now we'll move forward to update operations. I'll discuss the following that you can see on the screen. Unfortunately, due to time constraints, I'll only be able to get into the weeds of casual order processing, but I'll give brief overview on the other two. The update operation following casual order begins by the client sending in an update to the front end, and then the front end formulating an update request package that is sent to one or many replica managers. These packages contain a definition of the request operation or update operation, which is basically the type of what is being sent in, as long as with its parameters, the front end timestamp, and the update operation unique identifier, which is denoted as u.id. A replica manager, which we will denote as I, will receive the update request and proceeds to check its execution operation table and its log using the unique ID to see if the request has been processed or not yet. If it needs to be processed, we begin to promote the casual ordering by simply iterating the ith element in its replica timestamp by 1, thus meaning that the replica manager I has received another update in the current order. The manager then creates a log record entry for the current update log with all the information previously explained, as denoted here, along with TS being a new unique timestamp representing this specific update for this specific replica manager. TS here is extremely important because it's a derived value, meaning that no matter what, and every single time that we check this specific node, we will know for sure if this update has been seen here before or not. After this, like queries, the value timestamp information for this update is cross-checked with the front end's timestamp. Meaning that if this condition is not passed, we are not stable enough to send back, and we need to wait for new gossip messages to arrive and update this node until this condition passes. Now remember that these are not these are vectors, not single values, so we need to wait for all updates to catch up to this node that have led to the current update in order to be on time or more ahead of what the front end currently knows. That has basically led to the value of the current node that you're at. Once we're at this point, we will have already been able to apply the new update, but then we will also update the timestamp with the new value and insert the u.id or the update operation identifier to the set of executed operations to the execution table. Now for a brief overview of these two concepts. Forced and immediate update operations are requests into the system that need to happen immediately, minimizing block or wait time by prioritizing replica managers taking care of the request. This concept explores how to do this without ruining the order or in general hurting the availability of the system. Update propagation, on the other hand, is actually a very extensive subtopic, but it explores the idea regarding the fact that gossip architecture does not specify how frequent to send out gossip messages, or how a replica manager is supposed to decide which nodes to send its gossip messages to. Now for the real-world application, we're taking a look at Apache Cassandra. Apache Cassandra is a database system following Gossip Protocol that prides itself in high scalability and fault tolerance that puts it as one of the best platforms for cloud infrastructure and is used currently by GitHub, Instagram, Netflix, and many more. Cassandra adds greater sophistication to the baseline Gossip architecture by having coordinator replica managers that replicate around the cluster to nodes in the same zones. These zones, which categorize no state in order to replicate to the most relevant nodes first for greater efficiency. Cassandra also has consistency levels, which specify how many replica managers need to respond to the coordinator node in order to consider the operation a success. By not requiring all of the sent out replica managers to respond, an accepted update state for example, we improve latency and availability. At the same time though, low consistency levels will give less accurate data as it will not involve other replicas in the operation. High consistency levels, on the other hand, will decrease availability, needing more nodes to reach an accepting state and respond for operation success. Depending on the need per operation, we can tweak our consistency levels, or we can choose to use quorum writes and reads, which are briefly described here. With quorums, a read request can consistently give correct data, but only as long as the previous quorum write also worked perfectly. But in the case that the write failed, the system will expect all nodes previously said to have been updated to be trusted for accurate reads. Instead, the reads will find themselves seeing different values of data from the same zone, thus leading to extremely dirty data. Using quorums can be extremely good for short periods of times, and then very, very bad when the writes fail. This concludes our presentation on the Gossip Replication Control Protocol. Thank you.